Hey guys, so welcome to the episode 69 of the Eigenbros. So we have a special episode for our 69th. Sorry, I couldn't resist the meme potential, but no, we're doing a fun one on Bell's inequality.
Yeah.
So we talk a little bit about what do we talk about, Juan?
We kind of highlighted a bunch of like stuff that motivated Bell to kind of try to answer this question of basically quantum mechanics existing, coexisting with special relativity, and then almost like they're at odds with each other, and then try to see if the universe, like if entanglement is a thing that's real.
Right. And then we get into probability and, a little bit of all that kind of stuff, entanglement and stuff. Did you say entanglement?
Yeah, I did.
Okay, so then there you go. That's pretty much the extent.
No, but then the historical context of like Bell's theorem as well, like just and some little other neat tidbits about that. And then at the end, we kind of just discuss like our quantum probabilities and Bayesian probabilities, all these kinds of different flavors of probabilities. Like how those are real things in some sense.
Right. So cool, guys. Just make sure once again to like, subscribe, comment, share the video, and then check us out at eigenbros.com. Also check out the Twitter Eigenbros, check out the Instagram Eigenbros, and then TikTok Eigenbros too. And we'll see you guys in a bit.
3, 2, 1.
Hello, guys. Welcome back to the Eigenbros podcast once again.
Yes.
So as you saw in the intro, we will be talking about Bell's inequality. And pretty interesting stuff. Me and Juan actually learned about this, at least for me. I'll say embarrassingly, I only learned about it in graduate school. I didn't really know anything about it in undergraduate. I knew of the Bell curve, as people say.
Yeah.
But I don't even know if that's related to Bell's inequality, but...
Not really.
That's the extent of my Bell knowledge, besides Taco Bell.
Yeah, that's the only Bell that people outside of physics know.
Yeah,
like Bell. It's not Alexander Graham Bell. It's a different kind of. It's a different Bell.
What is Bell curve from?
Bell curve is from. It's some statistical thing. I guess it's the way it looks. It looks like a bell.
It's kind of ironic because Bell's inequality also has to do with a curve that's the same as a. Like bell curve.
I don't know. Maybe.
Yeah.
I thought the inequality was like just literally a mathematical quantity.
It is, but the big reveal, I guess, spoiler alert, is like instead of the tracing out the little sawtooth wave, not the sawtooth, but the triangle wave. It's a sinusoidal wave.
Oh, yeah.
And it looks like a bell.
Oh, I guess that is kind of ironic. Huh?
Yeah. So I was like, is this where Bell curve is from? And I was like, no, because the laymen don't know that. It's like a finance thing.
Yeah, that is true. I don't know. It was kind of interesting, like, because, we've had discussions about this, and then, like, modern physics is kind of built on this concept, this theorem, Bell's theorem, right?
A lot of modern physics research definitely utilizes Bell's theorem.
Yeah,
in quantum mechanics.
Like that. Reading about it, or just sort of like reviewing, just so we could have a discussion. About it, like, was kind of illuminating because, it made. How would you say? It made me realize how much of modern quantum mechanics is built on this, and then how much of the like leading theories are kind of pushing the boundary on this. Because for those of you that don't know, Bell's theorem says it's a sort of proposition by the gentleman. I forgot his name. I had it in my notes.
John Stuart Bell.
John Bell. Thank you. What a generic
From the
name.
Daily Show.
Sorry. Rest in peace. He died a couple years ago.
Oh, really?
Yeah, he got the Nobel Prize. He got the Nobel Prize for it, I think.
Oh, really?
Yeah.
Good for him. At least he got to see that.
Yeah, and it's because it's such an important result, because it kind of gives. Actually, I'm too much of a scatterbrain. I don't know if Terence, did you what did you synthesize from this? Because I have a thought about how to say it, but
there's a lot of info, right?
Yeah,
it's kind of hard to piece together. So, yeah, I feel like I could research this one for like a week straight and still be getting things out of it.
Yeah, same.
For sure. And I've been researching it for like years now. continuously. I'll just go back to it. There's a couple of good videos by Eugene Kudiansky. Also good videos by Arvin Ash and I want to say Mithina Yoganathan too. I can't remember if she has one.
Yeah, the PBS Science Channel as well has some good
yeah.
stuff on it. I remember watching it a long time ago. I mainly read for this.
Yeah.
Because I was like, man, there's so many cool little things. Like, I guess just defining it for the people listening, because we're kind of like ranting
beating around the bush.
Yeah, we are 7 minutes in and we haven't defined what we're talking about.
Yeah. They're like click.
So scatterbrained. I know we're so scatterbrained, but
this is kind of a discussion anyway. They're not really. There's many other videos where if you want to actually like learn about it and see good visuals and stuff, then that's for them. For us, it's more of like discussing how we feel about or what we think about Bell's theorem and all that kind of stuff, and what it may what it may entail, and et cetera.
Yeah, so for, I guess, just to give my quick synopsis of it, Bell's theorem says succinctly that honestly, like, the entanglement is a real phenomena.
Yeah. And basically, as opposed to the classical Einsteinian / Podolsky / Rosen thought that there's hidden variables involved. So let's, I guess, get into it a little bit. So let me define some things.
Sure, go for it. There's so many things to define.
Yeah, I know. So let's start with entanglement.
Yeah.
So I'm sure there can be some laymen here watching this video. You guys have heard of entanglement. It's one of these pop sci things that everybody uses now. It's been in Mass Effect and some other things. But entanglement basically says, like, you can have two particles essentially. So like a particle being an electron, even a photon. You can have two particles where they undergo something which it actually makes them entangled, I guess, for lack of a better word. And that meaning that they have some kind of correlation between each other. Mm-hmm. So the interesting thing is, though, it's a correlation that is undetermined. So, for instance, like the classic example is the spins of an electron. Mm-hmm. So if you have an electron that has a spin up, and a spin, like electrons can take on the values of spin up and spin down, right? But an entangled pair, they are correlated in such a way where if one has a spin up, the other one will have a spin down, but the person observing those particles does not necessarily know if the particle has a spin up or a spin down until they measure it. But then in quantum mechanics, once you measure something, that means you're actually collapsing its state into a finite value. So beforehand, it's in a superposition. You've probably seen that term as well, meaning that it's in a 0 and 1 state at the same time. I hate that terminology too because
there's so many problems with it.
But there's no other real good way to say it.
Yeah.
But it kind of means you're ascribing some kind of like interpretation automatically of quantum mechanics. Right. You say at the same time. But
yeah. You just say that the system is in a.
You can say it's in a superposition.
No. It's in. It has all possible states available to it. How about that?
Yeah. Okay, I like that better. It has all possible states available to it. So it's like when you mathematically write it, 0 and 1 have some probability associated with them. And then once you collapse it, that probability becomes 100% for whatever the 0 or 1 state that you measure is. Yeah. So it's weird. And you're like, but who says that it has to be at the same time, right? Yeah. Or what did you say, Juan?
It has all possible states available.
All possible states, yeah. Like, who says it has all possible states? And that's precisely the argument that Einstein basically said. He's like, who the hell is saying that it's got to be all possible states? Why can't it just be that we don't know what state it is, and there's some hidden other quantum number or something associated with this particle, in which once we measure that, then we can figure out what the particle actually has. Yeah. But with Bell's theorem, he basically proves that that's not the case. It's not hidden variables.
Well, this also comes, which is kind of ironic coming from Einstein, right? Because he's like one of the founding fathers of like quantum mechanics.
But Einstein's a true skeptic. He doesn't believe anything until it's like, for sure solid.
Yeah, because he believed in the idea of determinism, right? In some sense, like it's a very classical sense where you put the system in an initial state and it'll evolve dynamically according to a set of rules and principles, right? That are pretty linear in the sense that you can You like, for instance, like pushing a mass. That's a pretty linear process, and it's 1-to-1. You know what I'm saying?
Yeah.
But setting a quantum mechanical state in its initial state, and then you let it evolve in time, you won't get a linear thing. You'll get a probability of events. You get a probability of outcomes, right? Instead of a linear 1-to-1 thing.
So with a quantum system, it's all fundamentally probabilistic.
Yeah.
And that's just a weird concept.
It's a feature.
Yeah, because, in classical physics and even in general relativity, everything kind of makes sense, and it all has a deterministic approach to it.
Mm-hmm.
It's only when you start to get to the quantum regime you really start to see that reality is fundamentally probabilistic.
Yeah.
But then again, that's actually better to me, because that gives more credence to the fact that we do have free will, right?
Yeah.
Or at least, maybe I won't get down the super philosophical territory of that, but it implies that we have
that we can't tell the future.
Yeah, we can't tell the future.
Yeah.
100%. Let's say if the universe was deterministic, then down to every single minor movement, everything is predetermined.
Yeah.
But quantum mechanics gives it some fuzziness to where, you actually can have a little bit of uncertainty to things, and random things can occur, and it gives the universe some fuzziness where you can feel like free will might be safe.
Which is nice for those of us that are fooled into thinking we have free will.
Right.
Or at least,
right.
At least we have some semblance or an idea of free will. But
Yeah.
I tend to agree. I think it's probabilistic, but that could just be my own upbringing.
What?
In a
It's
sense,
probabilistic.
that I already accept that the world is probabilistic, and my own intuition about the universe is that it's probabilistic.
I don't know if you could get that unless you understood quantum mechanics, because really our universe doesn't really get probabilistic until you start to enter the quantum regime.
Well,
right?
you see similarities in. I don't know if this is built into life, but you see the similarity in biology, right? Where you get mutations happen almost randomly, in a sense. So you kind of see this chaotic process, but that's not to say that that's correlated with quantum mechanics at all. I mean, it might be.
But you're saying it's correlated with probability.
Yeah,
that makes sense. But I think that's a little bit different, because macro scale probability is just the fact that we cannot trace the long rabbit trail of deterministic actions to be able to see that it is non-random. It's like pseudo probabilistic in some sense.
There might be a case to be made for DNA being like mutations being quantum mechanic in origin. There was one of my old undergrad buddies. He was studying like something with like DNA polymers and how the chains follow, because there's certain bonds that are the chemical bonds are quantum mechanical in nature. Mm-hmm. And he was saying that there might be some quantum mechanical explanation for mutations in that sense to be probabilistic inherently through quantum mechanics. And it was kind of an interesting like hypothesis. I don't know what came of it. But it would be, if anyone out there knows, please let us know. That's an interesting question.
Yeah.
But yeah, I kind of gathered that before I got into physics, that the universe might be, there's an inherent probabilistic kind of nature. But I get what you're saying. It's not. It's a feature of like us not knowing the complexity.
Yeah. I think a lot of like probabilistic things can be down to that. Like imagine like with dice. Mm-hmm. You know, it's almost like if your dice, when you clearly see that when the dice is like loaded, you know, when it's like shaved on one corner, then you're basically you've changed it to where now it consistently goes to that side more.
Yeah.
And I think that has more so to do with the fact that if you can roll a dice perfectly your same way every time, then you can rig the probability to always go to what you want.
But that's kind of what Einstein was arguing, right? A little bit. Like the dice thing was like, it's kind of like we just don't have the amount of information, because the problem with probability is like the degrees of freedom. They're so large, right? Like you have 4 die or whatever, you have 2 die, and then you have like all multiple faces that you can get, blah, blah, blah. Mm-hmm. Isn't that kind of the argument? Like just because the system is more simple, it can be more deterministic. You know what I'm saying?
I don't really understand quite. I don't like the word degrees of freedom because I also don't really understand.
No, I'm saying like the amount of information in your system, if it increases, like like if you have one dice, right, and you have one number on the same, like let's just have one all over the dice, then you could say the outcome of that is just going to be one. So it's pretty deterministic when you roll it. It's just going to be one.
Okay.
But I'm saying you increase the degrees of freedom, so now it's that one. There's a number 2 on that dice.
Yeah.
But on whatever face. The thing is now you don't know. Now there's a the complexity is increased in a sense. You know what I mean?
Okay.
So now the degrees of freedom is like 2 or something.
Okay.
But you get what I'm saying? And then like now you have to account for the fact that each face has its own like number on it, and then you have to account for the fact that one of those numbers is number 2 and blah blah blah, and you have to basically but what I'm trying to say is you increase the complexity of the system, and that kind of like makes it harder to have a deterministic outcome is kind of what I'm trying to say. But I don't know, that's a thought.
Yeah, I'd have to think about that some more.
That's just
I don't really quite get what you're saying right now, but
maybe not. We'll see. Anyway, we're kind of
the God plays dice thing that Einstein says. Just basically saying he's just saying that I don't believe quantum is probabilistic.
Yeah,
he's saying that there's hidden variables, that there's something that we're missing or we're not seeing that is making this hard to. It's fooling us into believing it's probabilistic.
But that's kind of what I was kind of tying into with like me saying like Einstein thinks that we can simplify the system that like a rolling dice problem into something more deterministic. Like we could figure it out. We just don't have.
I think maybe the dice is the bad analogy. He just wants to make it a deterministic system.
Yeah.
Yeah. So something that can be reliably predicted every time. Mm-hmm. You know, if the particle is undetermined right now, he doesn't believe it's in all possible states. He believes that there's some hidden variable where the particle already knows it's in the spin-up state. And one of the reasons had to do with just because, you know, he's the father of general relativity and special relativity, right? And the whole thing with entanglement is when you entangle two particles, you can separate them at an arbitrary distance, but then once you measure one particle, let's say if we're looking at the spins again, right? When you measure spin up on one particle, there's 100% probability that there's a spin down on the other particle.
Yeah.
So it's almost like now that information has been instantaneously communicated. So if you have one particle on one side of the universe and another particle and an entangled particle on the other side of the universe, as soon as you measure that spin up state, it immediately gives the information, quote unquote, that it's spin down, which violates relativity because that means that information needs to propagate to that particle.
Yeah.
But of course,
it can't do it faster than the speed of light.
Right. It cannot do it faster than the speed of light because Einstein has shown that pretty much going faster than the speed of light violates causality. So it's like you can kill your grandfather, you know, which doesn't make sense, you know, because it's like you're fucking with time, which is not a good idea.
Yeah, like Einstein, I mean, that's why you see those world lines kind of thing. If you Google this for those listeners, you Google like world lines and light cones and shit. Yeah. You'll see physicists use these mappings to kind of give them an idea of whether your system is separated like space-like or like time-like separation or something like that.
God, you're going all
no. I just want to mention. I just want to mention it. I'm not going to go into it, but basically we have these tools to kind of give us a picture of if something violates known physics. And like in the case of
Minkowskian diagrams.
Yeah, the Minkowski diagrams. And like in the case of the EPR paradox that Terence is talking about with Einstein, Podolsky, and Rosen, the scenario that they came up with was if you have two twin particles or whatever, one on the other opposite end of the universe, separated long enough to where no signal can propagate or can reach them at a faster than the speed of light, right? You kind of run into this paradox, as they coined, that it's like, well, the information is being sent in faster than the speed of light in a sense. Yeah. But I don't know. One workaround that I remember, I had a discussion with a professor about this, and they were saying, well, no, there's no communication between the two.
Right.
Yeah. So it doesn't violate the signal propagation.
Right. And the reason being is the fact that, let's say if you wanted to communicate a piece of information, right? Let's say that your buddy, you send So you have particle A, and then your buddy has particle B, right?
Yeah.
And you say, well, if you get down, that means fire the laser or something. If you get spin down, fire the laser. If you get spin up, hold. But the thing is, like with particle A, how are you going to communicate that information? Because particle A, let's say it's in an undetermined state, when you measure it, you don't get to choose if it's up or down. So basically, that's a random piece of information that cannot be it cannot be made into information. Mm-hmm. So that's why people in physics have been kind of leaning towards like information as this fundamental unit somehow.
Yeah.
Of the universe. It's got some special property because, you know, although your buddy will know instantaneously what your particle is, and then his particle will also be, you know, instantaneously in some state 100% of the time, but you cannot manipulate particle A. You have no control of whether it's spin up or spin down. Mm-hmm. So no information is being communicated. Therefore, special relativity is not violated. Mm-hmm. So it's almost like a subtlety of the theory, and it still allows relativity to be consistent.
There's an interesting take that I saw. There were some people that were arguing for retrocausality.
What does that mean?
Meaning that like your system, say you have that same scenario, there might be a scenario where, because we're creatures of time, mm-hmm. the physics may allow for information to be sort of I had it written well in my notes, but I can't remember now. So it was just put succinctly, but the idea is that the system will adjust according to some sort of conservation principle happening. Like maybe let's just say conservation of information, like you're saying. That like the universe will, it's almost like an accounting, like because this system is up, the other particle in the universe is going to be down like that. And it's almost like if there is the universe takes care of it retroactively in some way, like it will almost rewrite the history in some sense.
Oh, does this have to do with like the super determinism stuff?
Yeah.
I saw that. A lot of physicists don't like this though, because then it's like so far. I mean, maybe it's true. It's almost like a headache to try to go down that path.
Yeah, it is. But it was interesting that some people were like, well, fuck it. We don't have any idea why are we trying to ascribe our notion of time onto these things? Like,
right.
We should maybe consider the following in a sense. Which is kind of neat. That's kind of a cool idea. I don't necessarily agree with it, but I just thought that guy just threw it out there.
Yeah. I mean, maybe, but I kind of like the interpretation that somehow information is this fundamental unit. You know, it also, for me, it opens up a door to a lot of new ways to actually look at
physics.
Physics, yeah, mm-hmm. because you can start looking at things as information. You know, and that kind of seems like a very modern take. You know, as well, because today we're such an age of information. And
much more fundamental than and it would be much more fundamental than focusing on
the specific particles and
stuff. Yeah, 100%.
Because you can apply that system to anything.
I've always found this incredibly powerful because it's something that I came upon maybe the year before I graduated my undergrad. It was 2015 or 2014. We had a class that a professor was talking about modern physics in a sense and all the contemporary things like Bell's Theorem and stuff. Mm-hmm. And so when we were discussing this, he'd brought up information and I was doing my own reading. We had an essay to do and
this is our class.
No, this was in my undergrad.
Oh, okay.
Yeah. But it sort of made me research a bunch of stuff and I came upon this idea that information was more fundamental and I'm like, man, I like where this is going because there's promising. I think you and I are fans of the abstract and more general solutions to things, and then
especially information because we're both in condensed matter, and basically condensed matter is the major application is computing, right?
Yeah.
One of them,
and it's crazy. I think it. Do you think it has it's holding validity, isn't it?
Yeah,
kind of. It's catching on.
Yeah, I think so. When we were talking about the Shannon paper the other day, that's kind of one of the big. To me, that was one of the big enlightening moments of oh, wow, you can do a lot with quantifying like how information is transferred or information, what's the smallest unit of energy to send information and all this stuff. Do you remember what the Shannon paper was fully called?
I looked it up the other day. It's something about some mechanical stuff. It came out in the
It was a while back.
I want to say 60s.
Okay.
I could be confusing it with the Bell paper, but yeah.
Well, Shannon's paper is this paper on basically information theory, and it's very, very useful and enlightening for anybody who's interested in information, or even if you're not, And I read it first when I was actually in fiber optic. So with the fiber optic field, I was trying to learn more about just like, it got me thinking more about like, what is information? And I just stumbled upon it randomly, and I was like, oh wow, this paper is very comprehensive and gives some nice explanations of what the basic units and like axioms of information can be. And I think that's a very promising and useful way to look at how, or I guess look at systems, in that kind of abstract framework to see like, what we can actually do in the future with information transfer or somehow communicating information.
Yeah, it was interesting because like, I think Eugene Wigner and a couple of these guys came up with a bunch of sort of thought experiments trying to answer the EPR paradox in some sense. And they were talking about superposition. And I remember them kind of getting into a fight about just what the hell is going on and what actually is being conserved and what isn't. And I think a lot of them came up to like information and being like, yeah, there's something more fundamental than just what we're talking about here with just like spin and stuff like that. There's something else happening that's more important to the universe in the grand scheme.
Right. It feels like a concept that has a lot of things to yield.
Yeah, and that might be a thing. I haven't read on modern papers, but we'll be having a discussion about this in the next episode more concretely about information and in terms of StatMech and stuff. So, because we had a buddy. Yeah.
Well, hopefully he'll come on. We don't want to say.
Hopefully he'll come on, but in the future there'll probably be an episode. More on this, but yeah. Anyway, like that was fascinating. But the thing that's did you read about the GWR theory?
No.
GWR
Woonified Riri.
No, GWR is like it was kind of interesting that it's a proposition that that tries to, because you get into this idea that, well, the universe, because how do I say this?
Is this related to Bell?
Yeah. Because Bell's theorem says, it almost exists in violation of relativity in some sense. At least that's the way Bell walked out of it.
Yeah. Like, it's not clear.
It's not clear. They're trying to you're trying to reconcile the two in some sense. That quantum mechanics exists in, like, how would you say, in spite of special relativity or something like.
Right. You want them to ideally to commingle somehow.
Yeah, but they don't. Like, well, nicely, not nicely.
I wouldn't. Yeah. Well, they're like loosely holding hands.
Yeah, it's like they're barely touching fingers.
Yeah, they're barely touching fingers. There you
and
go.
It's like, man, it's like, how do you have them where they just, they're nicely, they're playing nice. And
right. We want them strongly coupled together,
and just like, they might be different aspects of each other in some sense.
Right.
But we don't have that. They're clear, like, there's no clear like transition between them.
And maybe that's also a problem because we don't have a theory of
quantum
gravity, right?
Yeah.
So maybe that's like showing us that the picture's not complete.
It's not.
Yeah.
Like Penrose actually was one of the guys that I was reading about. He was trying to answer this. I'm going to go back to GWR, but Penrose was proposing that the reason why we get this kind of weird entanglement is due to gravity in some sense. Because nature doesn't like superpositions is kind of his argument. So he's like, gravity causes collapse, and you can read about it more. I think it's, you could just Google gravity causing like collapse or collapsing the wave function. And And yeah, they go into like a huge amount of theory that might help explain this, because they're trying to merge these two worlds together, or these two fields together. And I don't know if it's successful. I'm not in this field whatsoever. This is foundations of quantum mechanics stuff.
What was it? GWR?
GWR is this other theorem, but the one with Penrose is I think it's called the DW theorem, not from Arthur.
Arthur
DW. Yeah.
What does she say? Does
hey, or something. I don't know.
I thought she had a slogan or something.
That's how she ends the episode. Well, that's how she ends the intro.
Like, Arthur, you blockhead or something?
Yeah, I think that's right.
No, I think it's from something else.
No, I think
is it blockhead?
I think it's blockhead.
Okay, I don't know.
Could be wrong. but yeah, the
DW was a savage though.
She was, man. She was.
She definitely had the best roast on that show.
She kind of did.
There's a funny compilation on YouTube, but anyway.
No, it just made me think about Arthur. But anyway, the GWR theorem is another one that came out to try to explain this whole thing, and the best that they could come up with was that there's just like a spontaneous. They called it a spontaneous collapse or something like that. It's supposed to explain, like what we see, like the world exists as we see it. Like Bell's theorem coexists with special relativity, so there has to be some explanation that these two can coexist. And so GWR tries to explain that. And so you can read about all the details and stuff, but it exists. There's theories out there, and
can you give us like more than that, because that just sounds like regular physics to me.
Well,
saying that one theory
it's just more of an interpretation in some sense. Like it's like, how do you, because it's like you look at Bell's theorem, right, and you look at special relativity, and you know that these two like exist in the world around us. Like it's Bell's theorem holds, or inequality holds. Like our universe is, in a sense, non-local,
right?
As they've defined.
But do you remember the big takeaway? Like, what was the connecting piece of the interpretation?
I remember them not necessarily needing retrocausality to kind of explain it, but
I don't think we need that now.
Yeah, I mean, maybe
because that's the thing, is people kind of shoo away the whole violation of relativity. Remember, with basically saying that it's just information is not conveyed, so relativity is not violated. Yeah. So information is the fundamental piece really that matters in relativity. Because the whole claim of relativity that, you know, causality can't be violated is just because we haven't seen any instance of that. And it would just be such a screwed up world from our understanding that we just try to not let that happen, right? But there's no real strong statement besides that says that, at least that I'm aware of, that says that causality can't be violated, right? Like, I've never heard Einstein give a really strong reason of why that can't be true. It's just the fact that if you let that happen, then, you know, a lot of screwed up things are going to happen, and then a lot of the theory kind of general relativity wouldn't work as nicely, or maybe not work at all. So I don't know. I haven't heard a strong statement of why causality can't be violated.
Why causality can't be violated?
Yeah. We just generally don't like that, to think like that, because it's like then all kinds of paradoxes will occur potentially.
Well, that's in
but there's no
regards to
physical
time. Yeah.
But there's no physics reason or proof that I've seen of why that's not true. There's no mathematics I've seen where it shows in a very convincing way that causality can't be violated.
Yeah.
So my whole point was just that with that was just that the fact that Bell's whole inequality is not an issue because of that is because I'm sorry, what was I going to say? I'm getting all sidetracked now. You're on your phone.
I'm looking at GWR right now, and it's like because my notes, I tried to pull up my notes and didn't have it.
Oh, okay.
But
were you trying to get the scoop on what the big takeaway is?
Yeah, but it's a lot.
It's a lot to read, probably.
It's a lot to read. I will
Interpretations always are.
Yeah, that's the thing. It's an interpretation, so it's supposed to make these two things commingle, like you're saying, because we know that the quantum mechanics exists, and there's entanglement is real, which means that the universe is non-local in principle. Like, and what I mean by that is, well, what I think I had it in my notes, because
we should maybe talk about that locality.
Yeah, locality stuff.
So I guess I'll give a definition.
Well, first of all, realism, right? So when we talk about realism, it's like it's a philosophical point of view that says external reality exists with definite properties, right?
Right. Hold on. Let's slow down 1 second though, Juan. So you're kind of going into the stuff this is related to Bell's theorem again.
Bro. Yeah.
This is philosophy. This is like the territory of philosophy of physics, but you're going into something that's kind of useful for Bell too, because the Bell test has these three issues that people came up with. Basically, they're called the loopholes in Bell's inequality. So when you're doing experiments, these loopholes are something that you need to cover before your test is loophole-free Bell inequality test. And one of them has to do with what Juan mentioned earlier is locality. The other one has to do with realism. And then the other one has to do with the freedom of choice. So let's go into those a little bit.
Well, realism is like just the point of view that you kind of go in saying, external reality exists with definite properties, whether there's a conscious observer or not, right?
As opposed to there being like the quantum mechanical view of like something doesn't exist until we observe it, kind of thing. Right, and that isn't, and for people who may be confused by that, in quantum mechanics, there's this classic problem that every introductory student does called particle in an infinite potential well. And it just means like if you imagine literally like a particle in a box. So like an electron in a box, when that box is closed and you haven't interacted with that system, that particle can be anywhere in that box with a certain probability. Some places it can't be, and then some places it can be. But the quantum mechanical wave function gives you that probability distribution of where that particle can be in the box. So that's kind of a weird thing that we don't have to deal with in everyday life because I know exactly where Juan is. He's sitting right here.
My wave function is collapsed already.
Right. Well, yeah, your wave function is nice and set here. But in quantum mechanics, that particle in a box has a probability distribution of being in certain places in that box, and you don't know until you open it up and measure that box.
Yeah.
So when Juan says real, it means that things in reality have its definite place and position, and you can see it. And Einstein's classic thing is the moon, it still exists whether you observe it or not.
Yeah, he had this conversation with, who was it? It was I think it was, I don't know if it was Dirac or Bohr. I think it was Bohr. He was chilling with Bohr and they were having, and he's like, so you're telling me that if I look at the moon right now, it's not going to exist till I turn around and observe it?
Right.
He was like trying to roast his ass. Basically call him an idiot because he's like, you really think things don't exist until we observe them? Mm-hmm. And yeah, I mean,
and quantum mechanics kind of says like, I don't know, bro.
I mean, you have to question your. I mean, in the macroscopic sense, those things are already defined. You know what I'm saying?
But let's imagine this. Let's say nothing was interacting with the moon.
No, there's still energy in the system. There's still overall energy in
there's
the
energy
universe.
In a particle. Yeah, I'm saying let's pretend an empty universe.
Okay, but this is why. Okay. I don't know. I don't like this.
That's where you have to go. That's where you have to go.
I don't like this because it's already supposing that there are certain things that don't cause collapse. Okay, we're gonna get into a little argument here.
Okay.
But this is why I kind of agree with Penrose. Like, the gravity is a potential, right? It's already an energy that kind of might collapse wave functions. Might already put the system in a ground state, so to say. So it might already collapse everything as we see it, in a sense.
Right, because gravity exists because of massive objects.
Yeah.
And we already know clearly that gravity has like a field.
Yeah.
And, that field propagates at the speed of light, just like electromagnetic waves.
Yeah.
So when you have a gravitational pull, it literally, something is pulling.
It's always, your particle's always interacting with space.
Right.
Even then,
right.
at a minimum energy, but it's still interacting with massive bodies all over the universe and everything.
Right.
So I don't know.
But of course, we look at gravity as like the curvature of
space as well. So yeah.
But then again, now that got me thinking.
What?
Just now, because we tend to think of electromagnetic waves as having this speed limit, right?
Yeah.
Speed of light.
Yeah.
But if gravity is the curvature of space, I wonder if there's a way. It's weird that propagates at the speed of light too, because that's saying that space itself can't propagate at the speed of light. But we already know that space does go faster than the speed of light due to the cosmic inflation.
Yeah. I think.
So I wonder what the reconciliation is there.
Yeah, I think there's a paradox there that's been answered, but I don't remember.
Okay,
how.
Maybe.
I'm not
familiar. Just getting into cosmology.
And we're not cosmologists.
If there's any cosmologists watching this or astronomers, leave us a comment or something there if you understand that answer, because that's strange to me now. But I guess that also.
You're technically not traveling faster than the speed of light, I think. If we operate on first principles, it's like you're sitting on a wave front.
Yeah.
And it's imagine a surfer on the wave front, and you push the surfer. The surfer isn't moving; it's stationary, but space is moving.
Yeah, but I'm saying space itself is traveling faster than the speed of light. They've measured that with cosmic inflation.
But objects aren't moving faster than the speed of light. No massive body can move faster than the speed of light. I don't think it's...
Well, the object on the space is, though.
I don't think so.
They are. That's why people were confused by that, and that's why Einstein, had that whole thing where he called it his biggest blunder, whatnot, because he wanted to make the universe not expand. So he added in the cosmic, the constant in there to make it stationary, but then they realized that the universe is actually accelerating, and it goes faster than the speed of light.
Yeah. Well, I'm going to take cosmology next year, so...
Okay, well, you can answer this.
Maybe I can answer this.
Are you really going to take cosmology?
I think so. It's one of my electives, so I might as well.
Oh, so you're going to get those Einstein field equations finally.
I hope so.
Good. We can make a podcast on that so I can learn about them. Because I missed that in the undergraduate course we took. Yeah.
What a mess.
Yeah. Anyway.
So these loopholes, right? We get into you have to close these three loopholes to satisfy Bell's theorem. So Bell.
Right.
First of all, I think we still haven't defined Bell's theorem.
Bell's inequality. I guess we can real quick.
Yeah.
So basically, it's like this. So let's imagine this. So we've got a particle A. Mm-hmm. Particle A will decay into an entangled pair or something, or let's say we'll release an entangled pair of particles B and C. Particles B and C will go through two separate detectors that measure the spin of the particle. Mm-hmm. And let's say that the two spin detectors are aligned along the same direction, the same axis. So the spatialness of this actually is relevant, of the detectors. We always, just as an aside, I always wondered as a undergrad, and even as a graduate student, does the spin actually mean something spatially? But really, it kind of does and it doesn't. I know that's kind of confusing, but I like to think of it as like a binary kind of thing. But the spatial properties are kind of relevant in some sense.
Okay.
So what happens is when you measure particle B along one axis and then particle C along the same axis, you get different probabilities as those spin detectors are rotated. So this is where the spatial part actually comes necessary. Eugene Wigner has a very good video on this that I would definitely recommend if you want to search that. But then as you keep doing this and repeating these entangled sets going through these detectors B and C, particle B, let's just pretend like that detector is fixed spatially, but then particle C's detector rotates 360 degrees in space, or at least 180, because then that should cover the full Monty, if you will, and then the other side should be symmetric.
Yeah.
And that in the hidden variables test, each time you go through those detector, you have a certain probability to get either a spin up or a spin down, and that correlation between those particles. And as you rotate the detector spatially, your probability actually changes. And in the hidden variables interpretation, when you graph those probability points, so you're basically graphing probability versus the detector angle on an axis. So your probability is on y-axis, and then your detector angle is on the x-axis. As you graph that, you actually get a triangular waveform. Like if you guys are into synthesizer music, you know the triangular waveform. It literally just looks like a triangle.
Yeah.
But the interesting, that has to do with Bell's inequality. So Bell's inequality will give you that that graphical distribution of probabilities versus angle. Now, the crazy thing is, though, which is why this shows that quantum mechanics is a better model. It doesn't prove quantum mechanics is right, but it proves that hidden variables is not an acceptable interpretation in the sense that Einstein, Podolsky, and Rosen were talking about. Because actually with quantum mechanics, you get a different probability curve, and you get a sinusoid instead of a triangular wave. So it shows you that the probabilities are actually different as you rotate the detectors if the two spins, the two particles are in an undetermined state rather than a hidden variable state.
Yeah, and it's set up as an inequality, mostly out of like you read the original paper, and it's kind of a lot of math, which is surprising.
But it's very basic math.
Yeah,
it's like if you understand just normal algebra and maybe a little bit of statistics, you can definitely understand Bell's equality.
Yeah, but what I mean by math is like the level of abstraction, because they talk about particle states and stuff like that, and then you set up this like this assumption. I mean, this is a theorem, so of course you're gonna have math, but you set up this theorem, and so it comes out to where you have to have a value greater than 2 point something. Do you remember
2.93 or something, right?
Yeah.
That's for well, it gives you. It's like a trial. You can see that the sign when you measure the spin along the 45-degree angle. I think for both of them, I want to say with Bell's inequality, it shows you that it comes out with the wrong answer. It says that 1/2 is less than or equal to 0.293.
Yeah.
And that shows you that can't be right.
Yeah.
So that's the quantum mechanical. Those would be if you use the quantum mechanical probabilities, and they actually show you that Bell's inequality is wrong in quantum mechanics.
Yeah, which means it's sort of like we call this in math like a counterexample in a sense, right? To prove quantum mechanics is
something like that, or proof by contradiction. Yeah. It's along those lines. I don't know if that's completely accurate. We're not mathematicians. Don't shoot us.
On the terminology.
It's in that realm where it's like you can clearly do the experiment, and you'll get values that do not satisfy that inequality. Yeah. So it shows you that it can't be correct for quantum mechanics. But you actually
what do you mean by it can't be correct?
Well, it shows you that the inequality is not correct in the quantum mechanical model. That Bell's inequality is only for a classical model.
Right.
Yeah.
Okay, thank you.
Yeah.
I needed the audience to hear it.
Yeah.
Just so you kind of be like, what? Wait.
Yeah.
Quantum
Let's
mechanics
be very clear.
Yeah.
So quantum mechanics follows a different set of rules. It actually follows the rules that the particle states, the two coupled particles, are actually in an undetermined state. They do not have some missing variable that is hiding the information of what state they're in.
Yeah, it's a powerful little Bell's theorem is a powerful little thought experiment.
It is. It's really amazing too that you can actually distinguish with probabilities whether something is actually undetermined or if it actually has something that you just it knows, but it's just not showing.
Yeah,
it's very powerful. It just shows you the amazing, the amazing nature of probability and how you can actually get answers just by repeating something over and over and over again.
Yeah, fascinating stuff. Yeah. It's crazy. I mean, no wonder. Hats off to Bell.
Yeah,
he actually did this, and that's not to say that he got it right the first time. I think like he had several formulations of the theorem that had different iterations. So the original one was in 1964, and then one in 1971, 76, and then finally the one in 1990 was like the more well put together one. And it wasn't until recently, I think 2015 was when that landmark experiment was done where it closed all the loopholes, and that's why a professor made us do this paper.
Oh, really?
In grad school. Yeah, shout out to the.
I don't know if
professor.
anybody's ever closed all the loopholes. I think they've closed them mostly.
Yeah,
but I think the loophole one actually has an unclosable loop.
The 2015 paper.
I mean, not loophole, but the freedom of choice has an unclosable loop, I think.
Oh yeah. So explain the freedom of choice.
So that one I actually don't know.
That one's kind of interesting. Well, my takeaway was that the freedom of choice one is it has to do with like you setting up your experiment, how you set up your experiment, and whether or not you're setting it up in a way that's truly random in some sense.
Right. So people take the random information, let's say from like stars from like 600 or thousands of years ago, and they take the photons in that and actually use that as like
inputs.
Yeah. What do they call that though? It's like when you do your mouse movements on a computer and you can make your password stronger. They use that noise as like a seed to make more powerful passwords, and it generates random noise.
Gotcha.
I forget what it's called. There's a name for it. Leave it in the comments.
There's some function thing. Is it a kind of function?
Yeah, you can. But it's basically you can use random noise to make your stuff stronger. And that's basically what they use for the freedom of choice.
Yeah.
When they're actually measuring angles in those quantum systems, because they think that you might be biased. If a human does it, you're actually biasing the probability distributions. But lo and behold, the sinusoid that you should get from a quantum mechanical system still presents itself when you have a completely randomized thing.
Yeah, I think there was one interesting test in 2018. This was like 2 years ago, to like overcome this probability of having the deterministic nature of the outcomes or whatever.
Yeah.
One experiment used inputs from like over 100,000 people just to try to avoid this.
Yeah.
I thought that was
like a gamer thing or something.
Yeah,
right?
it was cool. Another cool thing that they did to remove, what was the second loophole you mentioned?
Local.
Yeah.
Locality.
Locality, which is like the physical separation between the experiments. So this has to do directly with like the speed of light. So like if you can say something, at least in general relativity, you can say something is space-like separated, I believe, if there's a signal that can't reach the other observer it won't violate the speed of light propagation being
basically locality, I guess the definition kind of is where it's saying that your system will not interact with anything outside of its local region. So it basically means like
by the speed of light, how fast.
Yeah, like it means like, so the fastest thing in the universe, of course, is the speed of light.
Yeah.
So your particle must. So if you have two particles in the universe, let's say the universe is just two particles, that one particle needs to at least be a distance of 300,000 kilometers away, which is how long it takes for light to travel 1 second, to have 1 second of locality. So it means that there's going to be no interaction with that system for 1 second. But then, of course, that got me thinking down a train of tangent where I was like, but then again, there's particles everywhere, so nothing's going to be local. But then I realized, okay, let's imagine if there's two particles together in the universe, separated way far, or there's three particles. So one particle in the center here, and then two particles together 300,000 kilometers away.
Yeah.
If you have two particles opposite sign, then all of that field should be canceled out except for the local region for those two particles far away. Does that make any sense?
Yeah.
So like if you have positive, negative, then it's neutral.
The whole universe is neutral.
Yeah. And you can look at that because if you zoom out on those two particles, then they look like one dot of a neutral atom, essentially.
Exactly.
And I was like, okay, it makes sense then. So as long as you have mostly neutral stuff around, then you should be good in your local region.
Yeah. That got me thinking too, like what's the longest distance we've gotten in measuring like
I think pretty far actually.
I want to say there was an experiment in which I thought was interesting. 2017. It was the longest distance recorded was 1,200 kilometers.
Oh, that's pretty good.
Yeah, it was achieved with satellite transmission.
Oh wow.
Yeah, so they did experiment.
Damn, no interactions with satellite. That's crazy.
I don't know. I mean.
So they were using photons to entangle.
Yeah, I'd imagine.
Makes sense. A lot of people use photons. And they entangle photons using the polarizations. Do you remember what that SPDC stands for?
No.
So they do some.
I'm not sure what that is.
There's some technique that they like to do with entangling photons. Let me just.
Yeah,
look it
well,
up
the
real
landmark
quick.
paper in 2015, I think, uses some kind of like it uses some kind of crystal to like polarize.
BBO.
I think so. I don't remember exactly.
That's the same technique. I'm pretty sure.
But that was like the landmark paper. If you guys want to go research it, just search 2015 Bell theorem test, and I'm sure it's like one of the main papers that came out.
Spontaneous parametric down conversion. It doesn't even sound like anything that makes sense.
It doesn't. That's
why I can't remember what it is, because I forget what the heck it even means sometimes.
Yeah, it's a weird abbreviation.
Yeah, but it's basically they make two photons pairing.
Yeah.
So the way I saw it was how did I see it? I think they have a pump electron or something that has some high energy that knocks another particle into another high energy state, but that particle cannot come down energies unless it releases two photons. So it releases a photon of high energy and then a photon of lower energy. But then that photon of lower energy has an exactly opposite polarization as the one with the high energy. And then they're entangled because of that, because of their opposite polarizations. But I think the uncertainty lies in which one has which polarization. I don't remember the details though, like why the polarizations are completely perpendicular.
Yeah.
But it's just a common technique, I guess, because it's very easy to do.
Yeah.
Because it sounds like it's like related almost to a laser in some sense, because you pump particle that hits something, I guess, it kind of gives it some kind of stimulated emission. Yeah. Except it's emitting two photons rather than one. But anyway.
Yeah, but this is all it's I mean, just kind of synthesizing everything, I guess. This was like I wish there were more foundations of quantum mechanics stuff like this going on. Probing a true understanding of quantum mechanics, right?
Right.
We haven't really done this. Like,
well, some people are.
Yeah, but it's like it's like is the right word eschewed? It's like eschewed.
Yeah. Eschewed, like they poo-pooed it.
Well, like
you eschew it, you poo-poo it.
Yeah. It's like the physics community is like, we're not really preoccupied with like
right.
Yeah,
shut up and calculate.
Yeah, and it's like we need to explore some of these philosophical quandaries within quantum mechanics. It's like this is all physics was initially motivated by philosophy in some sense.
I agree.
Or trying to understand the universe in some sense, because we reach these because the math can only get you so far.
Right. I think you're 100% right.
Yeah.
You need to have new insights from the philosophical implications.
Yeah. And Bell was kind of motivated by the Broglie-Bohm, the Bohm theory with like the wave packet thing.
Okay.
Because Bohm initially, his thesis was on, I believe...
Is that Bohmian mechanics?
Yeah. He was kind of like... Bohm was an interesting guy, but as a student, his thesis was basically born... It gave rise to the many world... No, that's Everett. I was thinking...
Okay.
But Everett was influenced by Bohm because Bohm wanted to create a theory that was like... that could have hidden variables, I believe. Yeah.
That's why I've been kind of careful to say like the hidden variables not completely debunk.
Yeah.
Because you can, I think, still have quantum mechanical systems that are aligned, I think, with kind of modern day ones like Bohmian. I don't know. I'm not familiar with Bohmian mechanics, but I knew his has something to do with hidden variables.
Yeah.
But the hidden variables of the Einstein-Podolsky-Rosen is moot. Yeah. Because theirs follows the whole Bell inequality.
Yeah. But rest assured, Bell's quantum mechanics is true. It's truer than true. It's a real feature of the universe. Entanglement is a real correlation between separated particles across space. So,
and actually, one I wanted to say too, I came up with a counter to shut up and calculate.
What's up?
So as people tell me shut up and calculate, for now I'm going to say slow down and contemplate.
Oh, I like it. That's a T-shirt right there. Slow down and contemplate, baby.
Yeah. So if anybody tries to give you that shit,
we need to fight back.
You got to say,
we got to fight back those people.
That's right.
Y'all suck, man. Y'all are stagnating the culture in some sense.
That's right. Philosophers of physics, we got to start taking it back because I think that's why we're in a rut too right now. can only get so far if you just keep shutting up and calculating. You got to have both.
Yeah. So
there you go.
Yeah. Hats off to Bell. Rest in peace. Legend. Modern legend of quantum mechanics. But is there any big takeaways, I guess, that you kind of wanted to share? I guess besides, like,
let me think. So,
any final thoughts, I guess?
Yeah, let me think. So, I don't know. I just the power of probabilities, you know, I didn't realize how powerful probabilities. It never really clicked to me, like, that probability is something that can be actually realized in real life too. Like, you can see its effect. Like, in the sense that, like, I'm saying, like, let's say if you had something that had a 60% chance of happening, or 40% chance of something else happening. So, like, an event A could happen 60% of the time, and an event B could happen 40% of the time. My old uneducated brain was like, well, then who cares? It's like it can happen either way or not. But the thing is, the whole power of probability is, if you do it enough times, you will guaranteed get it happening 60% more times, or 40% of the time.
Exactly.
When you actually look at a graph of all those numbers.
Yeah.
So you can actually get real numbers out of probability that you can test and look at, you know, if you do it enough iterations.
Exactly. Yeah.
So it just showed me, like, oh, like, and this is only a recent-ish thought, like, since I've been in physics, it's like, damn, I never realized how powerful probability actually is, and there are real numbers and things you can see from this.
And I'm going to send you down another rabbit hole, Terence.
Okay.
Because I've come to find, I was kind of shocked. I mean, when I realized probabilities were this kind of feature of the universe in some sense, I came to recognize, mathematicians started thinking about this. Are all probabilities created equal?
Like, what do you mean?
Like, are there different flavors of probabilities? Like, what makes, like, you know what I mean? Like, there's, and you'll come to find that they aren't. There are different kinds of probabilities, apparently. Like, Bayesian probabilities are one type. And then there are other more exotic types of probabilities that you can examine, which is a question that physicists were asking. They were like, well, what makes do we have, like, quantum probabilities, or just probabilities specific to quantum mechanics? Because the probabilities in quantum mechanics aren't the same as the probabilities in card tricks or fucking, like, rolling dice. In some sense.
Right. But I think the basic structure of probability is the same. But I think, like you're saying, I think the big distinction there is the fact of, are you taking into account all the variables that influence the probability? So with Bayesian probabilities, I know it's very heavy on, like, you can actually get different probabilities than you might think if you're analyzing it too simply.
Yeah.
So you need the actual variables that have some kind of heavy weight on the system to actually look at the probability properly. Like, I know the physics community has adopted a lot more Bayesian methods as of late. Like, even in our school, I know some of the professors use Bayesian probabilities in some of their research.
Yeah.
Because it gives you stronger results if you actually take in all of the factors. Like, let's say if you're, like, trying to find the probability of a dice roll, you know, we like to look at it as a pure thing where it's like, oh, 1/6 is always going to be the probability that you get a certain number on each side. But let's say it's a windy day, you know, you might use Bayesian probability by actually taking into account the wind factor of it. So then you might get a different probability distribution based on the wind, you know.
Accounted for,
Yeah, so it's like you have to actually look at all of the factors that are relevant to the system, and that's how Bayesian probability makes a stronger statement.
Yeah. So, yeah. I mean, that could be a discussion for a whole nother episode.
Yeah, you're right. I don't know much about probability, though, so that's, like, almost the extent of my knowledge.
We'd be opening a can of worms. We can maybe bring on some mathematician if they study probabilities and stuff in some sense.
That is one. There's always these handful of maths that I wish I knew more about.
Yeah.
And probability and, like, combinatorics, that's one of those big ones on my list that I wish I knew more.
Yeah, same.
Statistics in general. So
interesting.
Yeah.
Anyway,
that's our time.
Yeah, that's our time. We'll stay for the outro.
All right, folks. Thank you, guys. Thank you for watching. Thank you.
Thank you for staying. Please don't forget to like, comment, share, subscribe. Most importantly, share. And yeah, I guess a comment that we could leave. I guess we have multiple questions that we asked the audience.
Yeah, I guess so. What do you think? You got one in the bag?
No, I mean just the ones that we asked in the beginning, like
Yeah.
the cosmology thing.
Okay.
Or near the end, sorry.
Yeah, I say almost just, leave us your thoughts on this one, because this is such a big subject rife with a lot of good and interesting questions and dialogue.
Yeah, true.
Tell us what you thought of the episode. Tell us if you had something that you wanted to comment on, and we'll get to it. So leave us a message for sure.
Yep. All right.
And yeah, guys, make sure, once again, like, subscribe, comment, share, and then check out the website, eigenbros.com, Eigenbros on Twitter, Eigenbros on Instagram, Eigenbros2 on TikTok, and we will see you guys next time.